I'm Gary Pocock, and this is my week 13 reflection for the online modelling course. This week I'm going to look at the beginning of the magnetism unit and discuss a few aspects of the model that we're introducing in this unit. And I'll focus on the key differences between magnetic fields and electric fields and how we can best convey these differences to our students. And I'll look at some of the aspects on worksheet 1. Okay, well, one of the first things I really like about this unit is the way that they start with magnetic field going through a wire rather than starting the traditional start with bar magnets. I thought this is a really good idea. So right from the beginning, we are working on building a microscopic model for what is going on with magnetic fields and magnetic forces. So students are led to discover the very first crack in the course that a current moving through a wire produces a magnetic field. One thing I will comment on is on the diagrams in the modelling notes. They are starting to show their age, and this is one unit where good 3D diagrams can really help conceptual understanding. So I just grabbed this diagram from Google Images because I thought it was a nice one for conveying the magnetic field. And I thought it would be good if you could construct a question out of a diagram like this. So I fiddled with it a little bit and deleted the north pointing arrows and the compasses. And I'm imagining a question where we give the students the diagram on the left, first of all, with the Earth's magnetic field direction clearly marked. And we ask the students to draw north pointing arrows in the compasses in this situation where there is no current flowing. And once they've got that done, then we move on to a situation where there is current flowing in the wire. Students have learnt from the first lab the right-hand wrapping rule, so they know that the compass needle is going to experience a, looking down on it, we would call it an anti-clockwise movement. I think that's the right way to describe it. And so then they would have to redraw their compass, their arrows in the compasses to take into account the magnetic field of the wire. So I think that would be a much clearer question than the first question in the worksheet 1, which, well, that's the answers to it. So the first question in worksheet 1, which I've used this worksheet with my students, and they were struggled with this one because they were struggling to come to terms with the Earth's magnetic field, the rather confusing diagrams, and then working with the right-hand wrap rule as well. So I think an improved worksheet question along these lines would help a lot in that regard. Alright, now the second point I wanted to make is just staying on this lab. The lab is a bit daunting because of the current required, but I was very surprised to find that, and this is Derek Muller in his pre-Veritasium days, a very young Derek Muller, and here he's demonstrating lab 1, and he's actually doing it with a coat hanger. Okay, so no sounds coming through. That's the way I've connected it up. But that is a coat hanger that has been unbent. And he's just got a power supply, and he says it's only 2 volts. and yet he was still able to get compasses to move. I'm just looking for it. Can't find it now. Alright, here it is. So there we go. He's running 2 volts through a coat hanger wire, and he's getting the magnets to move. So I'm going to try that, because I think that's something that I can manage with my students. Alright, now the next thing I wanted to say is moving on to permanent magnets. Once we've done lab 1 and established that the current in the wire produces a magnetic field, and in particular we've established that these magnetic field lines form closed loops, then we can explore a bar magnet. Now, one of my real concerns I have is that the huge number of images around. So this is searching magnetic field bar magnet in Google Images. So many of them do not draw the magnetic field going through the bar magnet itself. So the vast majority of them do not show that magnetic field lines form closed loops. And that's a major problem, misconception that students can get if we're not aware of it. So I've just selected out one that does show that there are magnetic field lines of closed loops, consistent with what they have just discovered in relation to the field created by a current flowing through a wire. Not only does the field go through the bar magnet, but you can see that the lines are very close together, so the field is actually very strong. Strongest inside the magnet itself. And here also, you can see here that the iron filing demonstrations don't help either, because they show the field around the magnet, but they don't show the field inside the magnet. This diagram is much better because they've actually sprinkled the filings on the magnet to at least indicate that there are field lines happening on the magnet. Even with this one, even if they didn't have filings on the magnet, what they should have done is put compasses on top of the magnet as well to emphasize that it's a complete loop. Alright, so given that we're trying to build a model to explain magnetic fields in terms of moving charges, once we've introduced bar magnets, then we really owe the students at least some sort of explanation for how we can use using a moving charge model to explain magnetism in a permanent magnet. Fortunately, Veritasium again has done a brilliant couple of videos on this. Now this one here, where it's Veritasium and minute physics working together. So they actually go through the process of explaining electrons as tiny magnets, and then briefly explain the orbital situation, and then the domain situation, so we get to the point that certain materials are permanent magnets. I won't go through all that, but it's an excellent video. Not only do they do that, they connect to another video where, not that one, this one, where Veritasium does a brilliant explanation for how magnetism is actually due to a combination of electric forces and special relativity. This is so good. I shouldn't normally play videos, but this is so good. I'll just play a few seconds. No, it's not going to work. That's right. The way I'm set up, sound doesn't come through. But what he's got here is he's got a wire, and he's pointing out that the wire is electrically neutral, and he's got a positively charged cat sitting outside the wire. And then what happens, Okay, so this is the drift electrons. And then he asks, what happens if he gives the cat a little push? And now the cat starts moving, assuming the cat is moving at the same velocity as the drift electrons. And invoking special relativity, what you're going to get is length contraction. So the positive charges are actually going to, the distance between the positive charges is going to get smaller. The distance between the negative charges will get slightly larger because they're not moving relative to the cat. Hence, there is, in the reference frame of the cat, there is an overall positive charge. So the cat feels a repulsion and moves away from the wire. But of course, in our frame of reference, we can't see that electric force, so we explain it as magnetism. So I know that's beyond understanding for my students, but I still think it's a dazzling explanation, and it really gives them a taste of what's to come in physics. And I've shown this to a couple of my classes, and they can only understand a small amount of it, but they really do enjoy it, and they also importantly get the idea that there really is a subatomic level explanation for why bar magnets, or how bar magnets work, and why moving charges produce magnetic fields. Okay, some more images. Here I've got an image of a solenoid, and again, the modelling notes would really benefit, I think, from having improved images of magnetic fields. So when we get to the solenoid, I like to see it side by side with a bar magnet so that we can clearly see that the magnetic fields are identical, so that a solenoid is acting exactly like a bar magnet when the current is going through it. Okay, so the last point I'd like to make is about the Earth's magnetic field. Once again, there's a major problem with Google in that most images of the Earth's magnetic field, so magnetic field of the Earth, okay, they don't show the field lines going through the Earth. I've picked out a few that does show this. And it's good for the students to see this and to note how the direction of the arrows are going from the South Pole to the North Pole, which implies that our South Pole is a magnetic North Pole. So we can have a good discussion about that in relation to compasses. And lastly, just picking up on a point that someone brought up in the class, which I didn't know, I should have known, which is that compasses need to have little counterweights on them so that they can spin freely in their housing. If they don't have these counterweights, then the fact that the magnetic force dips into the earth makes the needle point down, and the needle can jam on the housing and not move freely. And so it turns out that one major compass company, manufacturer of compasses, has divided the Earth into 5 zones, and they put appropriate weights on their compasses depending on what zone they are in. So, me being in Australia, if I took a compass brought here to North America, I could have some problems with it. In fact, I came across one internet blog post of a chap who was a yachtsman, and he bought his nautical compass in South Africa, and then he went to sail to the Caribbean. He had major problems with his compass jamming for exactly that reason. So I think that's a pretty cool thing to tell the students.